2026 might be the year humanity stops visiting space and starts living there. NASA is preparing to return humans to the moon, not for flags and footprints, but to build the first permanent foothold beyond Earth. At the same time, a space station is being assembled in lunar orbit, and a nuclear-powered drone is preparing to fly across the surface of Titan. 3 missions, 1 roadmap, and together, they mark the moment humanity begins to move permanently beyond Earth.
This isn't another space update. It's the year humanity shifts from studying space to inhabiting it. What does that actually look like? We're talking boots back on the moon and the first steps of a permanent foothold. Here's the plan: how Artemis returns humans to the lunar surface, why a station orbiting the moon changes everything, and how a rotorcraft heads for a methane world to hunt chemistry that matters. Stay with me, because these aren't separate headlines. They're a single roadmap you'll be able to sketch from memory. If Apollo was a sprint and a selfie, why does Artemis 3 read like a building permit? Because the intent is different from the first line of the mission plan. Artemis 3 aims to land the first woman and the next man on the moon at a south polar site, where sunlight schemes the horizon for steady power and nearby craters shelter water ice. The goal isn't to plant a flag and leave. It's to set up operations in a spot with power access, thermal stability, and a local supply of volatiles that can be turned into resources. That means the landing site isn't a postcard location. It's chosen like real estate, with utilities and raw materials in mind. Apollo hopped down, collected samples, and blasted off after a couple of nights. Artemis builds in time, tools, and a path to repeat visits. Think longer surface stays with schedules for traverses, instrument deployments, and maintenance. Instead of one-and-done hardware, the plan leans on reusable elements that return for another cycle. Logistics isn't an afterthought, it's a requirement. You get power continuity, consumables planning, and checklists that read like field engineering, not a weekend excursion. And resource scouting is baked into the objectives, so crews don't just explore terrain, they assess whether it can support future missions. To land there, you need a specific stack. The human landing system uses a large lander with roomy propellant tanks, cargo capacity, and the ability to loiter in lunar orbit long enough to time a safe descent. The current path uses a Starship-derived lander that fills those tanks through multiple tanker flights in Earth orbit before it heads to the moon. That refueling campaign unlocks the Delta V for descent and ascent without redesigning the crew launch rocket. The suits matter too. A lunar-capable spacesuit with improved mobility, dust protection, and thermal control lets crews walk farther, kneel, drill, and carry gear without burning through resources. Longer EVAs turn the site from a stop to a workspace. The South Pole is attractive for 2 reasons that pair well. Peaks along crater rims see near-constant sunlight across a lunar month, so solar arrays can produce steady power and reduce battery and heater burdens. Just downhill, permanently shadowed regions trap water ice and other volatiles preserved for billions of years. That ice, if accessible, can be excavated and processed into drinking water, oxygen for breathing, and hydrogen-oxygen propellant. It's local fuel and air, sitting in deep freeze. Access both zones, and you trade shipments from Earth for a pipeline on site. You don't land blind. Cargo gets pre-deployed, a power kit, comms gear, and tools staged ahead of the crew. The lander targets a precise ellipse near resources to keep foot travel efficient and safe. Surface operations test life support stability under dust loads, verify that filters and seals hold up, and validate thermal systems through a full day-night cycle. Teams practice setting up rollout solar, clearing regolith from connectors, and keeping batteries warm when shadows creep. If something falters, the timeline allows troubleshooting rather than immediate departure. Science payloads reflect the new priorities. Crews carry drills that reach below the sun-baked layer to pull core samples with preserved volatiles. A mass spectrometer sniffs the thin exosphere and measures gas releases when regolith is disturbed or heated. In situ resource utilization demos heat icy soil and capture the vapor, proving flow rates and energy costs. Those numbers tell engineers how big a plant must be to support larger crews, and whether a given crater floor is worth the effort. Each checkout turns a visit into the first link of a supply chain. You drop navigation beacons that guide future landers to safe paths. You mark traverses that avoid sink-prone regolith and steep rims. You leave a relay that smooths comms to the dark valley floors. That's not a victory lap. It's a construction kickoff with assets meant to remain, so the next mission shows up to a site that already works. And if the ground becomes a job site, the orbit overhead has to become the warehouse, the staging lane, and the air traffic control. Why would a tiny station orbiting the moon matter more than a giant one circling Earth? Because it sits where the action is. Gateway lives in a near-rectilinear halo orbit, a lopsided path that swings close to the lunar south and hangs high for long, stable views. From there, it serves as the front desk, the tool crib, and the lab bench. Crews stage there before heading down. Logistics stack up there without needing to survive a landing. Instruments run in deep space conditions you can't get in low Earth orbit, like constant views of the polar terrain and long stretches outside Earth's magnetic shield. You might ask, why not go direct and skip the handoffs? Extra rendezvous look like extra risk. There's cost, complexity, and time. But direct flights tie you to narrow launch windows and force every ship to carry everything for every phase. Gateway splits the job into pieces. Landers can wait in lunar orbit, fueled and checked. Crews can arrive on separate rides and transfer when the timing is right. If weather or a minor fault delays one element, the whole mission doesn't fall apart. It's modular risk management instead of all or nothing. That orbit also unlocks flexible mission designs. Think tug and ferry. A solar-electric tug moves cargo with efficient thrust, while a chemical lander handles the quick sprint down and back. Because Gateway's path keeps long lines of sight to the poles, it can act as a comms backbone for surface teams tucked into deep shadow craters. And the geometry of that orbit shortens the wait for safe descent windows. You're not pacing an Earth orbit looking for a one-shot alignment. You're already in the right neighborhood. Early hardware sets the tone. The power and propulsion element brings solar electric propulsion for station keeping and high-efficiency repositioning, plus kilowatts of power for visiting vehicles and payloads. The Halo module provides life support, avionics, radiation sheltering, and the first crew volume. International pieces then extend the utility. A European-built habitat adds more living and experiment space, and a next-generation robotic arm supports external inspections, payload swaps, and lander servicing without a spacewalk if conditions don't favor one. Now picture the logistics loop actually operating. A cargo craft arrives first and locks in supplies, food, spares, batteries, and propellants. Crew docks later, checks systems, and moves into a rested schedule before descent. The lander cycles through the node, topping off, running diagnostics, and swapping filters and seals that hate dust. After the surface sortie, samples and fragile instruments stay safe at Gateway, cooled and monitored until a later ride can ferry them home without compressing everything into one splashdown window. Communications and autonomy tighten the loop. With delay-tolerant links, controllers can push software updates, queue commands, and receive bundled telemetry when line of sight shifts. Navigation aids tuned for the South Pole help landers thread between crater rims and boulder fields, and consistent uplinks keep crews in contact even when the sun angles go low. Medical teleops add another layer. With robotics and guided procedures staged at Gateway, crews gain confidence to extend EVA duration and handle minor issues without cutting a sortie short. Seen this way, Gateway is a rehearsal space for Mars. You test radiation shielding strategies against solar storms when shelter is days away, not minutes. You learn how hardware ages through months of thermal cycling without ground crew hands on it. You practice autonomy when delayed comms turn quick questions into planned decision trees. And you refine consumables planning when the next resupply isn't just a few hours chase around Earth. Put together, the station turns scattered missions into a network. Storage means spares on hand. Refueling means landers that work more than once. Schedule resilience means one slip doesn't erase a year. With that network taking shape, the map begins to stretch outward toward a new scout. The rotorcraft built to lift off in orange twilight and hop from dune to dune on Titan. 2026 ties the chain together. A lunar worksite starting up, an orbital hub coordinating traffic, and a robotic scout heading for chemistry that could inform how life begins. You can trace it end to end. Grab a page and sketch the roadmap. Artemis surface ops testing power, dust control, and resource handling. Gateway logistics stacking spares, fuel, and schedule margin. Then Dragonfly's launch window opening toward Titan's dunes and organics. Treat each milestone as one plan, not separate headlines. Mark dates. Track hardware handoffs. Note what carries forward. The shift isn't theoretical anymore. It's on the calendar. Watch it like a mission timer.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.